So this is Linda Sue Hoops, and I'm here to talk about expected values, covariance, and correlation. The expected value is another way of asking what is the average. So I have 10 numbers, I add them up, divide by 10, get the average. But if you notice, I have several 10s, several 12s, and several 16s. So I could do the multiplication first instead of adding, and then add those up and divide by 10. And then I could distribute that 10 across the numerator and turn each of those 3 over 10, 2 over 10, 5 over 10 into decimals, and I actually now have my expected value formula. I sum each outcome times its probability, and that will also give me the same as the average. So you'll look at the table here. That's typically how I would find the outcomes and their probabilities, and then I would multiply them together. But notice I don't know my original data in this table. I only know the probabilities and the outcomes. So that gives me the ability then to calculate the long-run average of an experiment that I've never even tried yet. So suppose you had a lottery for charity that costs $10 for each ticket. There is one $20,000 prize and 20 $500 prizes, and there are 10,000 tickets that will be sold. So here is my outcome table. I have the possibility of winning $20,000. That only happens 1 out of 10,000 times. I have a possibility of winning $500. That only happens 20 times out of 10,000. And I have a possibility of winning nothing, and that's the rest of the tickets. That will happen 99.79% of the time. So to find my expected value, I take each outcome times its probability and add them up, and I'll end up with 3. So over the long run, I would expect to win $3 for every entry. Unfortunately, I paid $10 for each entry, so that means I'm going to be losing $7 for each entry over the long run. So you can decide whether that's worth it or not if you want to enter the charity lottery, but it wouldn't be a good bet if you were trying to make money. The idea of covariance asks, well, how is age related to cholesterol? Ignoring the labels on the axis here, just kind of looking at the dots. Am I seeing an increase in good cholesterol as people get older? Am I seeing a decrease? Is it holding steady? I can't tell. Which one of those might be going on in my data? So I will calculate a mean, I'll calculate a standard deviation. I'll be using those in a minute. But let's look at our formula for covariance. So the covariance said I'm going to add up the difference between x and its mean multiplied by y and its mean times its probability. So as you can see in the graph, I have the 4 points that represent the age and the good cholesterol numbers. The dotted lines don't represent the x and y axis. They actually represent the mean. So the horizontal line would be the average of the x. The horizontal line, that's the vertical line would be the average of the x. And the horizontal line would be the average y. And then actually what I'm doing when I multiply those two together is I'm actually finding the area of those rectangles, the black and the red rectangles, and adding those up, and each one times its probability. So if I do the math there, you notice that my probability, I had 4 numbers, so the likelihood of each number was 25%. So then I multiply all those numbers together, and I get a value of 58. So I have a covariance of 58. However, if I were to change the units in which I measure one of those two things, so age is now measured in months. I know that's unusual, but this is an example. Measuring it in months, and I'm still measuring high cholesterol or good cholesterol, HDL, in the same units. Then I get a mean and I get a standard deviation. I go ahead and do the same math, find the difference between each and its mean multiplied by the 25%, and you'll notice I have 696. Well, if I change units, I get a different number for covariance. So that doesn't seem like a stable number. So I can take that idea and say, oh, now I'm going to do something called correlation. And correlation is just a scaled version of covariance. Just like z is a scaled version of the data value x, right? Because z is x minus the mean, and then you divide by the standard deviation. Well, the correlation between x and y is the covariance, which we know how to calculate, and then because we've already subtracted the mean of x and the mean of y in our formula, all we now have to do to scale it is to divide by the standard deviation of x and the standard deviation of y. So if I take my 58 and divide by the standard deviation of x and the standard deviation of y, I get 0.62. And I do it again with my months instead of years, and it turns out I get the same number. So that's good. And I would rather use correlation than covariance because it's more stable. So before we go further into an example, we're going to take our covariance formula and change it into a formula that's maybe easier to use. So first, we're going to take the expected value. So the expected value, remember, is going to be those x's, y's times the probability. So that's getting rid of the sum and calling it an expected value. And then I'm going to algebraically multiply those two binomials together. Notice that I'm going to then take through the expected value. So the expected value of each, that's a linear combination, is the expected value of each. But the expected value of x is the same as the mean of x. So I can replace that expected value with the mean, replace the expected value of y with the mean of y. And it turns out that then I have three terms that are the same except for the sign. So two negatives and a positive turns into one negative. So I have the expected value of x times y minus the mean of x and the mean of y, which I can also write as expected value of xy minus the multiplication of expected value of x and expected value of y. So using all the information we talked about so far, let's go back to expected value and look at our second example. So we have two common types of errors that computer programmers make. Syntax errors and logic errors. So if we're going to call x the number of syntax errors and y the number of logic errors on the first run of a program, then this is our joint probability mass function for a particular programming assignment. So to get the expected values, first we want to know what the marginal PDFs are. So if I want to know just what the expected value of a y at 0 logic errors, then if I just add up all of the ones in the row, then I get 77%. So ignoring all the syntax errors, which is x, I just look at the logic errors, which is y, and I go in that final column to the right. Similarly, on the row on the bottom, that would be just the probability of each one of those numbers of syntax errors, irregardless of what the logic errors are. So now to find the average number of syntax errors, I'm going to add up each one of the outcomes, the number of syntax errors, times its probability, which would be the marginal probability of the x's, and add them up. So I have a 35% chance of having some kind of a syntax error. Similarly with y, I have 32% chance of having some kind of a logic error in my first run of the program. So now let's look at the covariance, and remember I'm going to be needing the expected value of x times y, so that would be summing each x times the y times the probability. So now going to each cell in this table, I have an x of 0, a y of 0, and that happens 71% of the time. So I multiply the 0 times 0.71, etc. through all of the cells of the table, and I get a 35% chance of having both of them. So the covariance then would be the expected value of x times y minus the expected value of x times the expected value of y. So the covariance is 0.238. And again, that's not a very stable number, so we want to make sure that we find the correlation instead. Take it further to correlation. So we want the expected value of x squared and the expected value of y squared so that we can calculate the standard deviation of x and the standard deviation of y. So here would be the expected value of the x squared. So we just squared each of the x's, multiplied by their probabilities, and we get 67%. And the expected value of y would be 0.50. Going on to the correlation then, we're going to need the standard deviation. So we take expected value of x squared minus the expected value of x squared, and then take the standard deviation, square root of that. So I'll get 70.7399 is the expected, or the standard deviation of x. Standard deviation of y would be 0.6306. And the correlation then is the covariance divided by the standard deviation of x and the standard deviation of y. And substituting those numbers in, we get 0.51009, which means that the programmers that make more syntax errors are more likely to make more logic errors. So there is a positive moderate relationship between the number of syntax errors and the number of logic errors. In general, if our correlation is less than 0.5, it means there's a weak relationship. If it's between 5 and 0.5 and 0.8, it means there's a moderate relationship. If it's greater than 0.8, it means there's a strong relationship. And here is some general pictures of that. So a strong positive relationship would be going up. A strong negative relationship would be negative going down, which is why we have absolute value signs around our correlation. A weak positive would be a little more spread out, and a moderate negative, you can kind of see the trend, but it's not as tight as our strong negative. And of course, the none, you really don't see a pattern there at all. Be careful though, because there is a possibility that it isn't linear at all, and in fact fits more a different kind of function. So the only math we've done here is to find out if it is a linear correlation.